Welcome to The Explainer. Today, we're going to talk about a huge shift in how we build with AI. We're moving on from this fragile art of prompt whispering to a really powerful framework that finally brings some serious engineering principles to large language models. For the longest time, getting AI models to do exactly what we want has felt less like science and more like, well, some kind of dark art. We've been prompt whispering, fiddling with these delicate phrases, just hoping the AI gets the hint. The problem is, these prompts are so brittle they can break at the slightest change. And this whole approach, it's a total nightmare for developers. A prompt that works perfectly today might just completely fall apart tomorrow because the model behind it got an update. This lack of stability makes building and maintaining any kind of complex AI system incredibly hard. It's unpredictable. So this all begs a really important question, right? What if we could take all those proven principles from software engineering, things like modularity, reliability, automated optimization, and just apply them directly to building with LLMs? What if we could finally stop whispering and actually start engineering? And this is where a framework from the Stanford NLP group called DSPy comes in. It completely reframes the problem by using a powerful analogy that any programmer is going to recognize right away: the compiler. Okay, so check this out. DSPy does something really clever. It maps concepts we already know and use in traditional machine learning right onto this new LLM world. So in a framework like PyTorch, you have layers with numerical weights that get tuned by an optimizer. DSPy says, let's do the same thing, but instead of weights, our parameters are the prompts. The prompts themselves become the things the system learns. So here's the absolute key takeaway. You stop being a prompt whisperer, endlessly tweaking words. Instead, you become a programmer again. You define the logical flow of your application, and then the DSP compiler goes and does the hard work of figuring out the absolute best prompt to make it all happen. So how does this compiler magic actually work? Well, DSP basically throws out the idea of a simple text prompt and replaces it with three core programming concepts. These are the building blocks of the whole toolkit. First up, you've got something called signatures. The best way to think about these is like a function's type definition in code. You just declare the inputs and the outputs. A question comes in, an answer goes out. You're defining the what, not the how. You're not locking yourself into any specific wording just yet. Next up are modules. These are the reusable components that actually do the work. They're kind of like the layers in a neural network. So, for example, if you want the model to think step by step, you don't have to write a long, complicated prompt about it. Nope. You just use the chain of thought module. It's like a pre-built component for a specific prompting strategy. And finally, this is where the real magic happens: the optimizers. This is the compiler. It's the algorithm that automates all that incredibly tedious work of finding the perfect instructions and the most effective few-shot examples to get the absolute best performance for your specific task. Okay, so how does this compiler actually learn to write a great prompt? Well, the most common algorithm here is called bootstrap few-shot, and it's this brilliant process where the AI model essentially teaches itself how to do your task. Think of it like a teacher-student loop. The program, acting as a teacher, tries to solve a problem from your training data. Its answer gets graded. If it succeeds its own successful thought process, the whole reasoning trace gets saved as a perfect example of how to think correctly. It does this over and over, collecting the best of the best demonstrations to build the final optimized prompt. So before you run this process, your program's internal prompt is probably super generic, right? Just a simple zero-shot instruction. It might work, but it's probably not very reliable. But after compilation, whoa, that same simple prompt gets totally transformed. It's now automatically packed with these perfect, high-quality examples of how to reason, all of them tailored specifically to your data and your task. So finding good examples is already a huge leap forward. But the really cutting-edge research is pushing this even further. It's not just about finding the best examples. It's about getting the AI to rewrite its own core instructions. And this brings us to this amazing emerging algorithm called DSPy. It uses an approach that basically mimics biological evolution to systematically improve the actual instructions given to the model, not just the examples that follow them. So here's how this works. The system first mutates its instructions, trying out a new variation. If that version fails the test, a separate AI reflects on why it failed. For example, maybe it realizes, oh, it forgot to format the output as JSON.
Then, it uses that insight to evolve the instructions, creating a new mutation specifically designed to fix that exact problem. It's an incredible self-correcting, self-improving loop.
So what's the big deal here? Well, a framework like DSPy just fundamentally changes how we build with AI. It leads to way more reliable and predictable systems. It makes them portable. You can recompile your whole program for a brand new model, like going from GPT-4 to Llama 3 with just a single command. And most importantly, it moves the whole field from this quirky art of prompt whispering to the actual science of AI engineering. The end result is just a massive reduction in all that manual trial and error work that developers have been stuck with. The goal is to shift their focus away from the tedious job of tuning prompts and toward what really matters, designing the high-level program logic and letting the compiler handle all the optimization.
And this leaves us with a pretty fascinating final thought. By treating prompts not as some static piece of text, but as learnable, optimizable parameters, we've opened the door to automating a huge part of AI development. It really makes you wonder, if we can compile prompts today, what other complex parts of building AI are we going to be able to automate tomorrow?